Okay, we're going to be talking about the relationship between Ka, the acid dissociation constant, and Kb, the base dissociation constant. Now, if we take these two things together and we multiply them, we're going to get 1.0 times 10 to the negative 14th. And you might recognize 1.0 times 10 to the negative 14th because that is Kw. So Kw can equal two different things, and there's a reason for that. But this is a formula that's very useful because oftentimes we will not be given Kb, we will only be given Ka, and so we can solve this equation and use it to solve for Kb, which is needed in a problem. I will say as a side, if we did take the negative log of the Ka, negative log of Ka, what we would get is pKa. And if we took the negative log of Kb, obviously we would get pKb. And if we took the negative log of 1.0 times 10 to the negative 14th, we were going to get 14. So pKa plus pKb is equal to 14 as well, just like pH and pOH are equal to 14 as well. Now, let's do some application of using the Ka and Kb equals Kw expression to solve for some problems. So here's our first example. We're going to say that the weak acid HF, hydrofluoric acid, is going to have a Ka value equal to 6.8 times 10 to the negative 4th. And the question is, what is the Kb value for the fluoride ion? Now, just as an aside, just to remember, we talked about before how, if we took a weak acid and we reacted it with water, aqueous and liquid water, what we would get is we would get the weak acid donating its proton, or its hydrogen ion, to the water. And so we would get H3O plus, which we also know as the hydrogen ion, hydronium, and we would also get the conjugate base, fluoride. So in the Ford reaction being the reaction that's driven to the right, we would have HF being our acid and H2O acting as a base because it's accepting a proton. And on the reverse reaction, the reaction goes to the left, the hydronium is going to be acting as our conjugate acid, and the fluoride is acting as our conjugate base. So we say that the fluoride ion is the conjugate base of a weak acid, HF, even if it doesn't come from an HF, which we'll get into later. So that's the whole principle behind this. So either way, we can use this to calculate Ka. So we're going to, once again, we're going to use Ka multiplied by Kb equals Kw, 1.0 times 10 to the negative 14th. And so we're just going to plug our values in. We're going to solve this for Kb. Kb is going to be equal to 1.0 times 10 to the negative 14th over 6.8 times 10 to the negative 4th, which I get from the problem right here because they told me that was Ka. And we're going to go ahead and run that through our calculators, and we should get an answer equal to 1.5 times 10 to the negative 11th. Okay, let's scroll down here a little bit more, and we have another problem down here to look at. Okay, so here's our problem. We have Ka for acetic acid is equal to 1.8 times 10 to the negative 5th. And then we have Ka for HClO, which is hypochlorous acid, is equal to 3.0 times 10 to the 8th. So we're given two Ka values, Ka there, and for a different acid, Ka there. Both are weak acids. And the question being asked in part A is, which is the stronger of the two acids? Well, the stronger of the two acid is going to be whoever has the greatest Ka value. 1.0 times 10 to the negative 5th is greater than 3.0 times 10 to the negative 8th. So the answer would be the strongest of these weak two acids is going to be acetic acid. That's going to be our stronger acid. Okay. Now, the next question is, which is going to be a stronger base? And these are both conjugate bases of each of these weak acids, the acetate ion and the hypochlorite ion. So there's a rule of thumb that governs this, and the rule of thumb is the stronger acid equals or gives off a weaker conjugate base. So the weaker acid gives off a stronger conjugate base. And as we said before, the stronger acid was the acetic acid, so the acetate ion would be a weaker conjugate base. So the correct answer here would be, of course, ClO1 minus. Now let's find out if this is the truth, because we're being asked to calculate the Kb values, and we'll know which one is really which one's really the strongest and the weakest of the bases. So remember, Ka multiplied by Kb equals Kw, 1.0 times 10 to the negative 14th. And so for the acetic acid, it was given above, we had a Ka value for acetic acid as 1.8 times 10 to the negative 5th. And so we're going to plug this in for Ka, and we're going to go 1.8 times 10 to the negative 5th under 1.0 times 10 to the negative 14th equals Kb, and so I get 5.56 times 10 to the negative 10th, and that is going to be for the acetate, Kb for the acetate ion. Now let's go ahead and calculate Kb for the hypochlorite ion. Kb is going to equal 1.0 times 10 to the negative 14th over that Ka value that was given to us up above. Ka value given to us above was 3.0 times 10 to the negative 8th, and we divide those two and we get 3.33 times 10 to the negative 7th as a Kb value, and this is for the hypochlorite ion. So looking at this, we can see that the larger of the two is going to be a Kb value of to the negative 7th because it's larger than negative 10th. So the stronger base was the hypochlorite, which we predicted up here because stronger acids give off weaker conjugate bases. Okay, and that's tonight's lecture. Hope you have a great